It's my honor to introduce Professor Emily Pentzer to you. Professor Emily Pentzer is an associate professor in the Department of Chemistry and the Department of Material Science and Engineering at Texas A&M University in College Station. Professor Emily Pentzer received a bachelor degree in chemistry from Butler University in 2005 and a PhD degree in organic chemistry from Northwestern University in 2010, where her thesis work focused on metastasis routes for preparing and polymerizing unsaturated medium-sized lactones and lactams under the direction of Professor Solveig Nguyen. Professor Emily Pentzer then worked with Professor Todd Emmerich in the Polymer Science and Engineering Department at the University of Massachusetts Amherst, where she focused on the synthesis and the assembly of electronically active materials for organic photovoltaics as part of a DOE's Energy Frontier Research Center on polymer-based materials for harvesting solar energy. In 2013, Professor Emily Pentzer joined in the faculty at Case Western Reserve University in chemistry and received a secretary appointment in macromolecular science and engineering in 2015. Professor Emily Pentzer and her lab moved to Texas A&M University in the summer of 2019 as part of both the chemistry and the material science and engineering departments. Her research focused on organic synthesis to access new materials and assemblies as a route to understand structure, property, application relationships, and access functions not possible with current state-of-the-art systems. Today, Professor Emily Pentzer would like to give us a presentation on 2D particle surfactants and Pickering emulsions for reagent compartmentalization. Let's focus on Professor Emily Pentzer again and enjoy her talk.
Great, thank you very much, Yu, for that introduction. Move everyone around quick. There we go. And so I'm excited to tell you all about some of the work that my group has done. And we really view so I'm a chemist by training, as you said, and we really view emulsions as a platform to get a high degree of interface in systems, as well as to control the localization of reagents for different polymerizations. And so I'll start by thanking my group, who've just been really fantastic. They're shown here. We've had one person join since then, and no one's graduated yet, but we have students from chemistry, material science and engineering, and chemical engineering. And they've really been great to work with, in general, and then also through the pandemic, they've done an excellent job of being safe, but then also, continuing on their studies. And I'll also say that we really benefit a lot from collaborators and collaborations across campus and other universities. And so I'll try to point those out as we go through. And of course, we're thankful for our funding agencies. And a lot of our initial work on 2D particle surfactants started with the NSF Career Award. And so just to give you an overview of the type of research that my group likes to do, I've organized it into 4 different groups. The first one being active or functional liquids. And so that's, any liquid is functional depending on what you want the function to be. But what I really mean by this is non-aqueous and non-organic. And so we are working on the synthesis of fluorinated ionic liquids, so in which both the cation and the anion have fluorinated alkyl or aryl groups, with the goal of being able to use these to separate azeotropic fluorinated gas mixtures. And we're even looking at using some hydrofluoroolefins as starting materials for some of these structures. And then through an EFRC project, we're developing hydrogen bonded solvents as electrolytes, specifically for redox flow batteries. And the idea is these are kind of next generation ionic liquids where you don't need to do ion exchange, but instead you can just mix together a hydrogen bond donor and a hydrogen bond acceptor. So in this case, something like ethylene glycol and choline chloride, and you form a liquid that has a wide liquidus range. And our role within this is to synthesize redox active small molecules to either replace one of these components or which have a high solubility. And then we're getting into some redox active small molecules for microemulsions as well. On the more polymer synthesis side of things, we're interested in new building blocks for polymers or new monomers. And one of the platforms we've been working with are these silyl ketenes, in which basically ketenes have this orthogonal or accumulated double bond structure. They're not stable. They react with each other. And so when you put this trialkyl silo group, you get stability due to hyperconjugation and the beta silicon effect. And so our goal is to control the polymerization of the carbon-carbon versus the carbon-oxygen double bond with the big picture of getting a block copolymer or different polymers from the same monomer structure. And what ends up happening is we get a lot of secondary reactions and backbiting, and we are making some interesting small molecules as well. And the group is also working in additive manufacturing, so 3D printing. When we moved down to Texas A&M especially, we really kind of grew this area. And the idea of how do we use the composition of the filler and the curable resin to control the functional properties of the printed and cured material. And so far we've published using these for thermal energy storage as well as hierarchically porous structures to control the mechanical properties. We're now working on printing some of Don Derensberg's polycarbonates, for example, and looking at how microstructure within the printed object is different than thin film. So what we would expect based on just phase separation of block copolymers. But what I'll focus the talk on is our use of 2D particles at fluid-fluid interfaces. And so we're all familiar with emulsions. If you do organic synthesis and you do an extraction, maybe you get an emulsion you don't want, but they are part of our everyday life, from cosmetics to foodstuffs are probably the two most common areas in which we interact with these. And so we think of these as a phase separated system, so two immiscible liquids. So instead of the macro phase separation where oil is on top of water, if you put energy into the system, shear mix it, let's say, or sonicate, you can get droplets of, for example, oil and water. So these are typically kinetically unstable systems. And so we get the coalescence of the droplets in the macrophase separation, but we can decrease the interfacial energy and increase the kinetic stability or create steric stability by adding in surfactants. And so a lot of times we think of surfactants as these amphiphilic small molecules where we have a hydrophobic tail in the oil and then the hydrophobic or the hydrophilic group, head group at the water. And so in this way, we can stabilize droplets and prevent that macrophase separation. You can also use polymers as polymers as surfactants as well. And my group is specifically interested in using solid particles as the surfactant. And so in this case, we don't have an amphiphilic molecule, but instead we have a particle with suitable wettability that resides at the fluid-fluid interface. And so an example is silica particles, which if you just have as prepared or as purchased silica particles, they're covered with silanol groups and they're very hydrophilic. But you can alkylate those silanol groups and change the wettability of the particles. And so it's an even distribution of functionalization on the particles. And so depending on how many of this or what percentage of the silanol groups you functionalize, you can get particles from the same feedstock that are either residing more in the oil or more in the water. And so we envision these particle surfactants as being able to be more controllable about their location at the interface. They can also give improved stability to the emulsions because the amount of energy it takes to remove a particle from the interface is much higher than the individual molecule. And then we can also think about the particles that we use having functional properties. So can they actually do a catalysis, for example? And so our group really started looking at graphene oxide or GO nanosheets. And so these are dispersible in water. You can add in oils such as toluene and agitate by shear mixing. And you end up with droplets of toluene in a continuous phase of water with the GO nanosheets covering the oil droplet. And these are stable for weeks. And so we used this just as a platform for controlling where the reagents are, and did things like cross-linked the nanosheets, chemically cross-linked the nanosheets when they're at the interface to make capsules that we could then remove the oil on the inside. If we use an oil that's polymerizable, such as styrene, we can make a solid polymer particle armored with the geo nanosheets. And then we could also use this interfacial assembly of the nanosheets to selectively modify one face of the nanosheet with an initiator for ATRP, and then do a grafting from polymerization. So make these Janus type nanosheets. And this is really what started us down this road of using nanosheets at interfaces, but they're difficult to process because of the orthogonal solubility or dispersibility of the two faces of the nanosheets. And we've made capsules of phase change materials and polyalpha olefins, as well as use this as an approach for creating feedstock for selective laser sintering 3D printing. But I think our biggest contribution to this area has been just changing the wettability of those particles, of the geo nanosheets. And so in this case, alkylating the nanosheets. And so when we alkylate the nanosheets by reaction with a primary alkylamine, we change what solvent they're dispersible in. So they're no longer dispersible in water. And depending on the length of the alkyl chain, they can be dispersible in different oil phases, from polar oils such as DMF to non-polar oils such as octane. And so this really gives us access to these non-aqueous emulsions. And if you want to stabilize a non-aqueous emulsion, typically you end up making a block copolymer in which you have to, carefully tune the Hansen solubility parameter of the blocks, as well as the relative ratio of the two blocks. But here we're just alkylating the nanosheets to get them to be interfacially active. And so I'll talk a bit more about this, but from the standpoint of, we now have access to systems with a controlled amount of water. So they can be water-free, or they can have a controlled amount of water present. And we can use this platform and polymerization at the interface to prepare capsules, which have a core of whatever liquid was the droplet, and then a shell of polymer and nanosheets that can be isolated by filtration. And so to change the wettability of the nanosheets, my first PhD student, Brad, looked at reacting geo nanosheets with a primary alkylamines. The idea was we could get the ring opening of the epoxides on from both faces of the nanosheets, as well as acid-base chemistry with the carboxylic acids on the edges. And we do know that both of these reaction pathways occur from XPS. We can see in the nitrogen binding energy, we can see that we have both electrostatic and covalent modification. And so the idea was, if we have shorter chain alkylamine modified nanosheets, they're going to be more dispersible in polar oils, such as DMF or acetonitrile. Then if we use longer chain alkylamine to modify the geo, the nanosheets would then be more dispersible in octane. And Brad was able to show that he could indeed control the dispersibility of the nanosheets based on the length of the alkyl chain that's used. And I should say, with the bottom right here, these longer chain alkylamine modified nanosheets, they do precipitate out after 2 hours, but they're just dispersible for long enough in order to make the emulsions. And so if we consider that the continuous phase of the emulsion that we make is the solvent that the nanosheets are dispersible in, we could consider taking nanosheets dispersible in DMF, adding an octane and agitating, and we then access droplets of octane in DMF. Alternatively, if the nanosheets are dispersible in octane, we could add DMF, agitate, and then get droplets of DMF in a continuous phase of octane, as long as the nanosheets have suitable interfacial activity. And so Brad was able to show that he could form both octane and DMF and octane emulsions. So these are stable for at least 2 or 3 weeks, and which is dramatically different than if you have no nanosheets present whatsoever. We've done the control experiments where we just added in the alkylamines themselves, or the protonated form of the alkylamines, and they don't stabilize the emulsions. Something to note is that the C12 modified nanosheets are actually not very good surfactants and give emulsions that are only stable for a few days. And so Brad took the system and looked at doing polymerizations in these oil emulsions, or non-aqueous emulsions, with the idea being the reagent compartmentalization. And so if the continuous phase, so the green here is a monomer, so in this case, a tetrathiol and a dialkyne, and there's AIBN present, you could then do thermally induced thioline polyaddition polymerization and access a solid structure in which there are pockets where the droplets used to be, so a closed cell foam. Alternatively, provided we get mass transfer across the interface, if one reagent is in the continuous phase and one reagent is in the discontinuous phase, interfacial polymerization would occur only at the interface where those two reagents find each other. And we would then access a polymeric shell around the nanosheets. And then lastly, if we have a droplet that is composed of this isocyanate functionalized methacrylate, and again, some AIBN, we could heat this up, and provided the emulsion is stable, we could do this free radical dispersion polymerization and get a polymer armored with the geonanosheets. And so Brad showed that he could indeed access a closed cell foam, a hollow capsule. You see from the SEM on the right in the center that the hollow capsule is actually collapsed within the SEM. And then on the bottom right, he could also make these solid polymer particles. So he's cut the front end off of that particle to show that it is indeed solid all the way through. And so one thing to note is that the isocyanates on the methacrylate are retained after polymerization because we're in a water-free environment. And we know that they're there also from FTIR spectroscopy. And so here Brad's taken these solid polymer particles and seen if the isocyanate groups are accessible. And so he chose to functionalize them with this thiol functionalized coumarin dye. He could then get the addition of the thiol to the isocyanate and show that he could homogeneously modify the particles. And so we knew the isocyanates survived because we're in a non-aqueous environment. But I think this tells us some really interesting things, and we don't quite understand the organization of the nanosheets at the interface. But the big picture is that the nanosheets provide a barrier to droplet-droplet coalescence, but they still allow mass transfer between the two phases. And so this is seen both here in the ability to functionalize, isocyanates that we expected to only be in the polymer core, but also in the ability to do interfacial polymerization and make that capsule structure. And so we chose to leverage this platform in thinking kind of non-aqueous or non-water, non-oil droplets. And so in this case, turning to ionic liquids. And so some commercially available representative ionic liquids are shown on the left. They have a distinct solubilizing environment and applications across many different areas. They also have really high thermal stability and negligible vapor pressure. And one of their downfalls, or one of the difficulties of working with them, is they're very viscous. And so we envisioned if we could stabilize either droplets or capsules of these, we'd be able to use them in applications that the bulk ionic liquids cannot be used for. So using the idea of if we have geonanosheets dispersible in water, we could add an ionic liquid and stabilize ionic liquid droplets in water. And then alternatively, if we had the alkylated nanosheets, we could stabilize droplets of ionic liquid in octane. And so some ionic liquids are hygroscopic, and so you get a partition coefficient in slight miscibility. So the ionic liquid contains water and the water contains some ionic liquid. And so being able to use these non-aqueous emulsions gives us access to different compositions of ionic liquid. And so to make capsules in this case, so we can handle the liquid as a powder, we took the alkylated geonanosheets in octane, added in the ionic liquid in which we had added a diamine. We get the biphasic system, and then we use a little handheld emulsifier to shear mix this and access droplets of the ionic liquid with the diamine in a continuous octane phase. We could then add in the diisocyanate, and we're relying on the reaction to take place at the interface here. So we actually have to leave these for a couple of days, and we get this polyurea formation around the nanosheets at the interface. So we choose the polyurea chemistry because the monomers are readily available. There's no catalyst needed and there's no byproduct, but we are very interested in using non-polyureas to stabilize the capsules. And so we can draw this nice core shell type structure and say the ionic liquids in the core by itself. We can also filter these and isolate them. They look like dirt. So the brown color is due to the graphene oxide. From SEM, we see we do have individual particles. They have this rough surface morphology. And then if we cut the particle with the FIB, we end up seeing the core shell type structure here where the ionic liquid has come out after we cut the system, after we cut the capsule. We can also take the capsules on optical microscopy and press a glass slide on top, and we see the ionic liquid does come out. We can do this in the SEM. Case Western let us do this in the SEM where we actually poked it and the ionic liquid came out. And then we can watch this in real time. So here the capsules are in octane. And so this is a good one to watch where we press the sample on top and we see the ionic liquid is expelled from the capsule. And we do see a rupture here. So we're actually working with my colleague George Farr here to look at to measure the mechanical properties of individual capsules to see how much force we have to apply before we actually break the capsule shell. We can also extract the ionic liquid from the capsule shell using a solvent that the shell is permeable to. So in this case, we use deuterated acetone with mesitylene as an internal standard. And integration shows that the capsules are up to 88% ionic liquid. We can then compare the FTIR spectra of the ionic liquid itself to the capsules to the capsule shell. So after we've removed the ionic liquid, and we see that we remove the ionic liquid when we expect to. From Raman spectroscopy, we see that the characteristic D band and G band of the GO nanosheets, which indicates that the nanosheets are in fact in the capsule in the shell of the capsule. And from DSC, we see the similar thermal transition profiles of the ionic liquid when it's encapsulated as when it's in the bulk. And so this again supports that we have that core of ionic liquid rather than just some polymerization throughout the capsule and ionic liquid plasticizing it. And then from TGA, we see a slight decrease in the thermal stability of the ionic liquid upon encapsulation, but this is common when you mix ionic liquids with anything. And so we use these for a number of different applications. And in all instances here, we're relying on the fact that the shell is permeable to small molecules, which is interesting in its own right, because normally if you put nanosheets in a polymer, what ends up happening is you decrease the permeability. But in this case, we're actually seeing really good permeability. But here Yifei and Chinmo took the capsules and loaded them into a column with the idea that we could then pass oil that had been contaminated with phenol through the column, and the phenol is soluble in the ionic liquid, so it would go through the capsule shell, and then the eluent would be that phenol-free oil. And so we compared the ionic liquid filled capsules to the capsule shell by itself. Here's a little pipette column that they made. And basically we see that we are actually making use of the ionic liquid upon encapsulation. You could also envision using the polymer chemistry of the shell to control the permeability and selectivity of the removal as well. In a collaboration with Professor Burju Gherkin at Case Western Reserve University, we looked at the CO2 uptake, so of the ionic liquid when encapsulated versus the ionic liquid when it's neat. And so ionic liquids have a high solubility of carbon dioxide, and so, but an issue being that in order to make use of that high solubility, you have to have a high enough surface area. So you typically have to mechanically agitate the ionic liquid in order to reach equilibrium of the system. So we envision that, again, provided our polymer shell was permeable to the CO2, that we would be able to hold the, or to have the capsules unagitated and make use of the ionic liquid on the inside for CO2 uptake. And so this is just a generic ionic liquid, I should say. And so if we look at the uptake capacity for the shell by itself versus the capsule versus the agitated ionic liquid, we actually see our capsule shell is really good at uptaking carbon dioxide. So again, there's opportunities to play with the chemistry. But if we subtract out the contribution of the capsule shell, we see that the ionic liquid uptakes the same amount of CO2, whether or not it is encapsulated and unagitated or bulk and agitated and stirred. And then the yellow data here shows that if we have the ionic liquid unagitated, we actually never reach equilibrium. And so while this was promising, we also found that the time that it took to reach equilibrium for CO2 uptake was actually significantly less, or it happened more rapidly for the capsules than it would for the agitated ionic liquid. And so we think there's essentially plasticization of the polymer shell with the core material, and that facilitates mass transport. We've since gone and shown that we can use a task-specific ionic liquid where you have a chemical reaction with CO2. We've also demonstrated that the identity of the polyurea shell does impact the CO2 uptake capacities. And so I'll tell you now about some of our current directions. We're interested in other polymers within the shell. And so Yifei actually, I said, well, what if you can, make these capsules, you treat them individually, individual capsules, and then can we, destroy the polymer shell, or can we fuse them into a monolithic structure? And so for that, Yifei turned to hindered urea bond chemistry, a type of dynamic covalent bond. So if you have an isocyanate and a primary amine, they react, they form a urea, very stable, and they typically decompose before any reverse reaction is observed. But if you use a secondary amine where you have a tert-butyl or an isopropyl group on the nitrogen of the amine, and you do form a urea, but because of that bulky group, you have it causes the urea bond to not be planar. And so that decreases the activation energy needed to undergo the reverse reaction. And so depending on what that bulky group is, for example, if it's a tert-butyl group at about 35 degrees, you can actually reverse the urea bond formation to produce the isocyanate and the secondary amine. So the idea was by incorporating some of these hindered urea bonds into the capsule shell, we could then either compact the capsules and heat them up above that, the temperature needed for the bond reversion, and we could then have cross-linking between capsule shells. Alternatively, if we take the capsules in the presence of a primary amine, so hexylamine in this case, and we heat them up upon the reverse reaction, the isocyanate that's formed ends up getting siphoned off by the primary amine, the hexylamine, and we then destroy the capsule shell. And so Yifei showed that she could indeed access both of these reaction pathways. And these are just for oil and oil emulsions. She's done it for a number of different monomers. But what she observed was when there was ionic liquid in the core, she actually could not isolate stable capsules. And we attribute this again to the plasticization of the shell with the ionic liquid, which provides a more polar environment and really decreases the temperature for that reverse reaction. And we've done variable temperature and MR to show all of these things. Another current direction we're going is using a non-graphene oxide based particle surfactants. So this is a collaboration with Professor Micah Green, who we have a joint student, Huishen, and MXenes are transition metal carbides or nitrides or carbonitrides. And so a representative chemical structure is shown on the top right. The big picture is you have this titanium carbide nanosheet, and it's decorated with different functional groups. So based on the synthetic method, these are normally fluorine, OH, and these bridged oxygen species. So MXenes are typically made by taking a max clay. So luckily my Colin Mladen Radovic is an expert in making new max phases, but here we just use a very I would say traditional max phase. And you treat this with HF and lithium chloride normally, which removes the aluminum from the interlayers, and then you treat it with DMSO, some mild sonication, and this delaminates the nanosheets. And so MXenes have a negative zeta potential. They're dispersible in water. And so we just took a page out of the clay playbook from a few decades ago and just added in salts such as sodium chloride, which flocculates the nanosheets, so overcomes their steric repulsion between the negatively charged nanosheets. We then add in toluene in this case and agitate, and we access our emulsions that are stabilized by the salt flocculated MXenes. And we can use the same interfacial polymerization I talked about with the geo nanosheets to make capsules. We could remove that inner oil phase, and the capsule shell is composed of both MXenes and polymer. And in this case, MXenes, I should say, have a propensity to undergo oxidation to give TiO2. And so in this case, we're protecting the MXenes from oxidation. We can also do that dispersion polymerization where the oil, in this case, is styrene, make these MXene-Armored particles. We see the flaky morphology here. Then we can, because we're not cross-linking the polymers, we could hot press them together and make these films, if you will, with a relatively high conductivity on both the surface and the cross section. We see the particle, the residual morphology from the particles. And we showed that these underwent, because of the conductivity of the MXenes, underwent rapid RF heating and could also be used for electromagnetic interference shielding. And so we're also using cobalt oxide nanosheets. So with Alp Shahar Liou at Case Western, we've developed chemical methods for the exfoliation of cobalt oxide nanosheets. We can make larger nanosheets than we could before. We can also, make these cobalt armored particles and use these to activate a catalyst for oxidation of bisphenol A in water. The last thing I'll tell you about current direction is using the nanosheets to stabilize gas bubbles. And so we call these Pickering bubbles. And so in this case, Peyron and Al tried a number of different things. And I'll say that we ended up using these fluorinated gas bubbles as dual ultrasound and photoacoustic imaging agents. And we haven't really tried to stabilize any other gas bubbles, but it should be reasonable to do based on the functionalization of the nanosheets. So Al and Peyron took the nanosheets, tried a number of different modification scenarios. This is what worked. So they did an EDC coupling of the carboxylic acids on the edges. We do see a darkening of color of the nanosheets, which supports that we've chemically reduced the GO, so removed the oxygen functionality and reinstated carbon-carbon bonds. We could then exchange the air in the head space out for perfluorinated propane, agitate, and then make bubbles of perfluorinated gas armored with the GO nanosheets. And these are relatively stable. They're stable for a couple of hours. We could think about chemically cross-linking these to make them more stable. But again, we're not exactly sure of the organization of the nanosheets on the surface of these. So hopefully what I've told you about are that 2D nanosheet surfactants are interesting to access different compositions of emulsions, and those can be used to architect a number of different structures. We're working on making polyhypes, which are high internal phase emulsions after polymerization of the continuous phase, as well as measuring the permeability into and out of the capsule based on using small molecule dyes as the markers. And there's more, but I'd like to stop there to allow plenty of time for questions. So thank you very much for your attention.
Thanks for Professor Emily Pentzer's great talk. Students and postdocs could ask questions firstly. May I ask my first question? I'm very curious if it's possible to remove the geo layer or geos after the polymerization to get porous, pure porous polymer shell.
So I don't think so. We have not tried the geos there, but we're definitely not forming a tortuous path through the shell, and so we haven't tried to make any porous shell. We're relying purely on permeability as well. But starting this, we said it was, why do we want to use the nanosheets? And I was thinking we would make really mechanically robust capsules, but it turns out that's not the case. And so, but we haven't tried to, but I don't think we could remove the nanosheets.
Okay, gotcha. Thank you so much. Students and postdocs, do you have any questions? If students and postdocs don't have any questions, faculties, please feel free to ask questions.
Actually, I have a quick question, if you don't mind. Actually, I
yeah, sure,
Alex's hand up. I was wondering if you can just elaborate a little more on that example where you showed improved CO2 uptake in those capsules versus just the agitated ionic liquids on their own.
You mean, why do we see improved?
Yes, sorry.
Yeah, no, that's just fine. So we don't understand the difference in rate, I guess, of up in the time it takes to reach equilibrium. So we know that residual amines within the capsule shell can help. So amines react with CO2. So like aqueous amines have long been used to uptake CO2, but it's clear that they pass the CO2 to the center. So it's not like we clog up the shell, if you will, with CO2. So we're actually working, we call ourselves Team CO2, but it's a group from Bridget at Case Western, and then Alyssa Park at Columbia, and Michelle Kidder at Oak Ridge, and Rachel Getman at Clemson, to actually understand the transfer of gases from outside the capsule to the shell to inside, and then getting it back out as well. Because anytime you get something to go in, especially if you have ionic liquid in the core, right, it's going to be way too expensive and not anywhere near sustainable unless you can get it out with low energy input. So we're a great question, and I hope to be able to answer it.
No problem. Thanks.
Alex, I see you raise your hands.
Yeah, thanks you. That was really cool, Emily. Thanks for the talk. I was curious to hear a little more about the purification you described that removed phenol. I thought that sounded neat, especially from a lab that doesn't love column chromatography. So what works well for those kinds of separations? What are the challenges? You know, it'd be fun to hear about how you think about sort of expanding that and what the opportunities in that area are.
Yeah, so the big thing is you need something that is that the shell is permeable to, and that is more soluble on the inside, on the liquid in the inside versus what it's already soluble in. And so we've used capsules with a core of polyalpha olefin to extract BTEC, so benzene, toluene, ethylbenzene, and xylene from water. And so that's a pretty kind of low hanging fruit because, the solubility is so different. And so what we're doing now is actually measuring, we're getting into chemical engineering, a field of, what's the flow like, what's the particle size, what's the column packing density. And so in order to understand that better, we're actually doing experiments where we have a dye on the inside and looking at the rate that it comes out into water versus into water of different pHs, for example, versus into water methanol mixtures. And then also looking at it going into the core. And so I think we have to answer a lot of really fundamental questions. And, we could also look at the permeability of the polymer by itself. But an issue with that becomes that we have such a small thickness of the polymer. The polymer is so thin that it's not quite like having a bulk polymer film. But we're trying to come at it from that fundamental understanding of permeability.
That's super helpful. And is there any hope for like recycling the beads afterwards?
Yes. So we can heat it up to get out or pull vacuum to get the BTECs out of the PAO, but that energy input has to be low enough. And so with Team CO2, we're for gas regeneration, so CO2 coming out, we're looking at like RF heating, so using the polar domains within the inner liquid, I guess, for localized heating versus convection heating. You could also think about putting it in another solvent in which whatever the contaminant it'd be like A to B and then B to C. You could think of something like that. The other thing I'll mention is that we are using these as additives for direct ink, right, 3D printing, so we can actually make a structure where we have a high density of beads. So kind of go from a liquid that's hard to handle to a powder that may be easier, but still kind of a pain sometimes, to a monolithic sample that we could stick in as a wand, and then pull out. So we don't have to rely on columns.
Thanks.
Is there any questions?
I have a question. Nice talk, Emily. I think you mentioned that your shells can actually allow penetration of small molecules. And I was wondering, would it be possible to tune the size of molecules that can go through the shell?
Yeah, so we're not really relying on size exclusion. And so with the dye, we're also looking at obviously charge. Because we're, while we are, using, I guess, the free volume within the polymer shell, it's not necessary. There's also the enthalpic interactions, right, between the molecule and the polymer. So that's helping it go through. We could think about, and we have thought about, but haven't done anything with, the idea of, using such a polymer of intrinsic microporosity. So we actually have porosity to the shell. And then we could think about size selectivity, but we are relying on permeability, which is different than porosity.
Due to the time limitation, I think we could take one more question. Anyone have any question?
Okay, I think he'll be in, room I'm talking
Okay, if there is no question, let's thank Professor Emily Pentzer again, and thank everyone for participating in the webinar hosted by our NSF Center for Integrated Catalysis. Now, participants, please feel free to leave. Paula, our director, will host our next session.
Yeah, thank you. Thank you, Emily. Nice seminar.